Our next topic for discussion is pumping lemma. Pumping lemma for context-free languages. When we looked at pumping lemma for finite automaton, this was our intuition or an idea. You choose a string of length at least n, in particular a large string, and this string you can decompose them into u, v, w, and this has this property that z is part of L, and you find that u v square w belongs to L, u v cube w belongs to L. In particular, for all I greater than or equal to 0, u v power I w belongs to L. So if you choose a string which is really long, in particular at least n, you see that with that you can generate infinitely many strings which are part of L. Okay. In particular, we say we pump V once, twice, thrice, and so on. So from the automaton perspective, if you see, you get to see that something like this. Now this part of the automaton reads U, and this part of the automaton may be a self loop, or you get to see a couple of states and then come back here. This part of the automaton reads V, and this part of the automaton reads W. This picture itself tells you that U, V, W is part of the language, U, W is part of the language, U go via this once, again via this, so which means U, V square W is part of the language, and so on. And so if language is regular, then this property is respected, and we used the contrapositive of this to show that certain languages are not regular. Okay, so the idea is the following. In an attempt to understand or talk about non-regular sets, one should understand regular sets. And in an attempt to understand regular sets, we look at a sample automaton or a string accepted by the language, and then we observed certain properties out of it. And those properties were helping us in coming up with something like a pumping lemma. And the contrapositive of that statement helped us to show that certain languages are not regular. On the similar line, what we are going to do for context-free languages is the following. Choose a string sufficiently long and then come up with a similar decomposition by looking at the properties of context-free languages. Fine. So the idea is the following. In this case, we will be looking at the grammar, not the underlying pushdown automaton, because both are equivalent. Suppose you have a derivation for a string. When I write like this, through sequence of one or more productions, you reach a string, say U. And we want to look at the string U. We say that this U can be decomposed into V, W, X, Y, Z. For a finite automaton, we say it is 3 components, but for CFL, we say it can be decomposed into 5. Okay, so you can look at it this way. Suppose in this derivation, okay, so somewhere a non-terminal A appears. Before this you have something, after this you have something. So A is a non-terminal. A is a non-terminal appearing in the derivation of u. Let's assume A implies we have W A Y, this is one production, and we also have A implies X. Okay. So let's assume A appears at least twice in the derivation of U. Okay. Because we are taking sufficiently long string, and which means you will find the non-terminals appearing as part of the derivation. Correct? In particular, I am saying the non-terminal A is appearing twice, and one production is like WAY and another production is A imply X. Okay, so which means if you look at U, and U was derived starting from S using these productions, right? So you get to see that at one point A will be replaced by WAY, and at other point A will be replaced by X. Okay. So let me repeat this part. When you start deriving U starting from S, naturally you will find some non-terminals appearing in the derivation. So what we say, let's assume the non-terminal A appears at least twice in the derivation of U. And one production says A implies WAY, and another production says A implies X. So first application, what I do, I substitute WAY. Before that and after that, something is there. In the second application, I substitute A implies X. Okay. Now something to the left, something to the right. Let me call this as V, this as Z. Okay. Now this is part of the language because this is how we have derived. Now instead of A implies X, you apply WAY again. So you get WAY Y, which means this becomes W square A Y square like this. Now you apply X. So you get W square X Y square. This I call it as V, this I call it as Z. Now you see that this is also part of L. Now you apply this WAY couple of more times. So you get to see that W power I, A, Y power I. In the next application, you say W power I, X, Y power I, this. And to the left, let me call it as V, to the right, we call it as Z. You see that it belongs to L. So what are we saying? You choose a string and say U, and in the derivation of U, you see that the non-terminal A is appearing twice, at least twice. And let's assume A implies WAY, A implies X. Then you see that if you apply once, we get VWXYZ. And if we apply twice, we get this. And we keep applying this, say, I times, then we get this. Fine. So this says that if we choose a string U, and which can be rewritten as VWXYZ, then you see that v w square x y square z is part of the language, and you keep applying this I times, then v w power I x y power I z belongs to L. Okay. So the idea is the following: a sufficiently long string has two substrings w and y, which can be pumped any number of times. For a finite automaton, a sufficiently long string can be decomposed into three components, in which you find exactly one component which can be pumped any number of times. So there is one component which can be pumped any number of times. For a context-free languages, you find two components. One is W, the other one is Y. W is a substring, Y is a substring. And they both can be pumped any number of times, and resulting strings are part of the language. So given this, one can generate infinitely many strings which are part of the language. This is just the top level picture. There are details. So the larger message is the following: you take a string of sufficiently long, something like there exists an integer n such that cardinality of u is at least n. Then, very similar to this, you can come up with a decomposition respecting some constraints. We shall see that constraints now. It is that constraints, and that will tell you that yes, such a decomposition is possible, and you can demand that for all I greater than or equal to 0, v w power I x y power I z belongs to L. Okay, so there are a couple of things. One, what we choose must be a really long string, and then decomposition satisfying some property. Okay. Now we shall write the pumping lemma very similar to finite automaton, and we shall see a couple of applications and so on. The proof of this follows from given a context-free grammar. Look at the underlying binary tree, meaning convert that into Chomsky normal form. Look at the underlying binary tree. In the underlying binary tree, you can observe that there will be two subtrees, one for W and another one for Y. With that, this argument comes. Okay, but I am just outlining the top level picture to show that a sufficiently long string can be sufficiently long string has two substrings W and Y, which can be pumped any number of times to generate some more strings which are part of the language. Okay, so this information is enough for us to discuss a couple of examples. Let's get into that. Here is the lemma. Let L be a CFL, then there exists an integer n, okay, such that for all, let me use the same notation, such that for all u belonging to L, cardinality of u is at least n. So this tells you that u is a really long string. So for all u belonging to this, such that u is at least n, u can be decomposed into 5 components or 5 substrings. So there exist v, w, x, y, z such that u is v, w, x, y, z, and very similar to finite automaton, we demand wy is at least 1 and wxy is at most n. Then for all I greater than or equal to 0, v w power I x y power I z belongs to n. Okay, so this says at least one is non-empty. At least one of w or y is non-empty. So both simultaneously cannot be empty. And this portion length must be at most n. So what this says is the following. CFL implies the following. There exists an integer n such that for all u, and cardinality of u is at least n, implies there exists v, there exists w, there exists x, there exists y, there exists z such that u can be written as v, w, x, y, z, and wy is at least 1 and wxy is at most n. Okay. With this, for all I greater than or equal to 0 implies that u w power I x y power I z belongs to n. So this is only one way. If it is context free, then this is respected. Now, similar to pumping lemma for regular sets, we will be using the contrapositive of this. Okay, so what this says is CFL implies pumping lemma. Negation lemma implies negation CFL. Okay. So now we will be using the contrapositive of this to show that the given there are languages which are not context free. So which means we choose a string and such that string length is at least n. Then we say whatever way you decompose, this will become negation of this, right? So whatever way you decompose for all v, w, x, so on, respecting this constraint, there is one I for which the string pumped is not part of the language. That shows that our assumption that it is context free is false. Therefore, the given language is not context free. Fine. So a sufficiently long string has 5 substrings such that 2 of them, w and y, at least one is non-empty, and this middle portion w, x, y is at most n. Then you can generate some more strings that are part of the language. However, for the application perspective, what we will be doing is we will look at the contrapositive of this, which means for a given language, to show that it is not context free, we will choose a string respecting this constraint, and we say whatever way you decompose respecting this property, here is one I for which the string generated is not part of the language. Okay, so that's how the application will be. So the larger message is the following: if you choose a string of length at least n, and it is a really long string, right? So which means as part of the derivation, some variable must have occurred twice in the derivation. Okay, which is why we said let a appears twice in the derivation. Okay, because it's a really long string. So which means some variable must have appeared at least twice in the derivation. Then we closely look at what all you can derive from that non-terminal. We said one of them might give you WAY and another one will give you X. The moment you apply X, you stop. And if you keep applying WAY, you will keep getting WAY, W square, AY square, and so on. That's where the pumping happens. Okay, and so with that in mind, here is a formal description. Now let's use this and show that there are languages that are not context free.